Greetings, everybody. Learning is a hobby here. I want to go over my solutions to the exercise set for section 5.5 in Tao's analysis one book. We're almost done with chapter 5. I know it's taking me a little bit longer to finish chapter 5 than it took for chapter 4. I explained why that was in my vlog for the month, so I won't go into it here. But we're going to finish up the exercise set here for section 5.5. Then we have only one more section left to go through in Tao, and then we can get back to Spivak. So let's go ahead and not waste time and just jump right into it. So here's my solutions. Let me just move some things out of the way on my screen. Okay, so first question, 5.5.1 says this: let E be a subset of the real numbers R, and suppose that E has a least upper bound M, which is a real number. In other words, M is the supremum of E, which we defined in the summary for section 5.5. Let minus E be the set defined as the set of all negative X, where X is an element of E, and we want to show that minus M is the greatest lower bound of minus E, or in other words, minus E is the infimum of negative E. So here's my proof. Right, let E be a non-empty subset of the real numbers, or actually, I don't think that was part of the it just says subset, so it could be empty. Let E be a subset of R with least upper bound M, then X less than equal M for every X in R. Then negative X greater than or equal to negative M for all X in E. That's just a property of real numbers, if you remember. That implies minus M less than equal minus X for each negative X in the set negative E, which implies that minus M is the lower bound for minus E. Assume there is some epsilon greater than 0, such that minus M plus epsilon is also a lower bound for minus E. Then that minus M is less than minus M plus epsilon, which is less than or equal to minus X for all negative X in the set negative E. Then X is less than M minus epsilon, which is less than M for all X in E, which contradicts the fact that M is the least upper bound for E. Therefore, minus M is the greatest lower bound for minus E, or in other words, if M is the supremum of E, then minus M is the infimum of minus E. Okay, that's the first question. Then the next three questions are actually referred to in the summary, in my section summary for theorem 5.5.9. I elected to leave the proof for that theorem to the exercise set because Tao, in writing down his proof, it's really more of like an outline of a proof, because he asks the reader to prove a bunch of things along the way. The next three exercises here are part of the things that he asks you to prove along the way. So at the end of the exercise set here, after we go over all the exercises, I'll finally prove theorem 5.5.9. But anyway, let's get through these first. So let E be, this is the question. Let E be a non-empty subset of R. Let n greater than or equal to 1 be an integer, and let L less than K be integers. Suppose that K over n is an upper bound for E, but that L over n is not an upper bound for E. Without using theorem 5.5.9, show that there exists an integer L less than M less than equal K, such that M over n is an upper bound for E, but that M minus 1 over n is not an upper bound for E. He gives a hint here. He says prove by contradiction and use induction. He says it may also help to draw a picture of the situation. We're not allowed to use theorem 5.5.9 in proving this because we don't want our reasoning to be circular. We're going to use this to prove theorem 5.5.9, so we don't want to use the theorem to prove this lemma. So that's like circular reasoning, right? So we want to do it without that. Anyway, let's get to my proof. So let E be a non-empty subset of the real numbers. Let L and K be integers where L is less than K. Then L less than K implies there's some M in Z such that L less than M less than or equal to K. That's just a property of integers, right? Assume K over N is an upper bound for E and L over N is not for some N. For some non-zero natural number, and we induct on the distance between K and L. In other words, K minus L. I'll just to give it a name, I'll call it D for distance. So here's our proof. It's by, like I said, induction on the distance between K and L. So here's the base step. D equals 1. If k minus L is equal to 1, that implies that k is L plus 1. Then L is less than L plus 1, which is equal to k. And L over n less than L plus 1 over n equals k over n. Therefore, therefore the integer m, this is bad English that I have written here. M over n equals L plus 1 over n is an upper bound for E, and m minus 1 over n equals L over n is not an upper bound for E. I guess I should say that, therefore, there exists, just to be proper, to have proper English here. Therefore, I guess I could say it like this. Therefore, m is an integer. That's one of the things. I'll just leave it like that. Whatever. Okay. Then we go on to the inductive step. Assume the proposition holds for some distance d in the natural numbers minus 0, or in other words, d is a non-zero natural number, right? That's the distance between the two integers k and l. Then for any integers kl, where k minus l equals d, and k over n is an upper bound for E, but l over n is not, there is m in z such that l less than m less than equal k, where m over n is an upper bound for E, but m minus 1 over n is not. Right? Consider all k prime l prime in z with l prime less than k prime, and k prime minus l prime equals d plus 1, and k prime over n is an upper bound for E, but l prime over n is not. Assume there is no m prime in z with the specified property. So I'm going to do this by contradiction. Then k prime minus l prime equals d plus 1 implies k prime equals l prime plus d plus 1. Then L prime less than L prime plus D less than K prime. Either L prime plus D over N is an upper bound for E, in which case the inductive hypothesis implies the existence of an M prime in Z, such that L prime less than M prime less than equal L prime plus D less than K prime, where M prime over N is an upper bound for E, but M prime minus 1 over N is not. That's a contradiction. So therefore, the only other option is that L prime, sorry, I'm getting tongue-tied here. Otherwise, L prime plus D is not an upper bound for E, in which case M prime equals K prime is an integer with the specified property, which is a contradiction. Since these two cases are the only possibilities for L prime plus D, the proposition holds. And again, this was a proof by induction, so therefore the proposition holds for all non-zero natural numbers by induction. Okay. Next exercise 5.5.3. Let E be a non-empty subset of R. Let n greater than or equal to 1 be an integer, and let m prime be integers with the properties that m over n and m prime over n are upper bounds for E, but m minus 1 over n and m prime minus 1 over n are not upper bounds for E. Then Tao wants us to show that m equals m prime. This shows that the integer m constructed in the previous exercise is unique. And again, he gives a hint here. He says, draw the picture. That might be helpful just to get some intuition. All right, here's my proof. Assume for the sake of contradiction that m is not m prime, then m is greater than m prime or m is less than m prime by trichotomy. Without loss of generality, we can assume that m is less than m prime by symmetry, right? Then m prime minus m is greater than 1, implies m prime greater than m plus 1. Then m prime minus 1 is greater than m, implies m prime minus 1 over n is greater than m over n. That contradicts the fact that m prime minus 1 over n is not an upper bound for E. Therefore, it has to be equal to m prime. And that's the proof. Right, next one, 5.5.4. This is the last part that we'll use for proving theorem 5.5.9. There's still one more exercise after this, though, and then we'll do it. So here's the question, 5.5.4. Let q1, q2, q3, dot, 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 be a sequence of rational numbers with the property that the absolute value qn minus qn prime less than equal 1 over m, whenever m is greater than or equal to 1 is an integer, and n prime is greater than or equal to m. Show that q1, q2, q3, dot, dot, dot is a Cauchy sequence. Furthermore, if s is equal to the formal limit of the qn as n goes to infinity, show that the absolute value m minus s is less than or equal to 1 over m for every m greater than or equal to 1. He gives us a hint here as well. He says use corollary 5.4.10 or exercise 5.4.5. I use corollary 5.4.10. So that's, you'll see in the proof that that's what I did. Okay, so here's my proof. Let epsilon greater than 0, then there is m in n such that 1 less than equal m epsilon. That's just by the Archimedean property. Furthermore, for any n prime greater than or equal to m, absolute value qn minus qn prime less than or equal 1 over m by hypothesis, which implies that absolute value qn minus qn prime less than or equal to 1 over m less than or equal to epsilon. Since epsilon was an arbitrarily we chose epsilon as an arbitrary positive rational number. That means that the sequence qn is a Cauchy sequence, since it's eventually epsilon steady for any epsilon. All right, next, let S equal the formal limit of the Qn, then let M greater than or equal to 1. Then for n prime greater than or equal to m, the distance between Qn minus Qn prime less than or equal 1 over m by the previous part. In particular, the absolute value Qn minus Qm is less than, excuse me, is less than or equal to 1 over m for all n greater than or equal to m. Then Qm minus 1 over m is less than or equal to Q sub n, less than or equal to Q sub m plus 1 over m for all n greater than m. Define two, and then here we'll define two new sequences. So we'll define a sequence an and a sequence bn, where an is equal to the constant q sub m for all n greater than or equal to 1, and bn is q sub capital M plus n for all n greater than or equal to 1. Then those two sequences are Cauchy, since an is a constant sequence, and bn we constructed from the tail of a Cauchy sequence. Also, the sequence of absolute value an minus bn, and going from 1 to infinity, is a Cauchy sequence, and m greater than or equal to 1 implies the constant sequence 1 over m, and going from 1 to infinity is Cauchy. Lastly, the absolute value an minus bn less than or equal to 1 over m for all n greater than or equal to 1 implies that the formal limit as n goes to infinity of the absolute value an minus bn less than or equal to the limit of 1 over m as n goes to infinity, which implies that the absolute value qm minus s less than or equal to 1 over m by corollary 5.4.10. And maybe I should show you what that corollary says just in case people don't remember. Let me see, 5.4, where is that? What was it, 5.4.10? That's this one here. So let an and bn be Cauchy sequences of rationals such that an greater than or equal to bn for all n greater than or equal to 1, then limit an going to infinity greater than or equal to limit bn going to infinity. So that's what I used at the end to prove that. He also says you could do this using this other proposition here. I didn't use it, but you might, find it fun to try doing it using this instead. Proposition 5.4.14 says, given any two real numbers, x less than y, we can find a rational number q such that such that x less than q less than y. So, but I used the corollary. So, okay, and that's the last of the lemmas that we'll need for the proof of theorem 5.4. Sorry, I need a drink of water, I think. Sorry about that. Okay, that's the last of the lemmas that we need for the proof of theorem 5.5.9. Here's the last exercise, though, and then we'll get to the proof of the theorem. So question 5.5.5 says, establish an analog of proposition 5.4.14 in which rational is replaced by irrational. Proposition 5.4.14 is the one I just read to you guys. That's this one here. So he wants us to replace, in this theorem, he wants us to replace rational number with irrational number. All right, so here's my proof. Let x, y be real numbers such that x is less than y. Then square root of 2x less than square root of 2y implies there's a rational number q, not 0, such that square root of 2x less than q less than square root of 2y implies x less than q over square root 2 less than y. If q equals 0, then there's some q prime in q such that x less than 0 less than q prime less than y by proposition 5.4.14. So we can always find a non-zero rational q that has that property. Then, okay, then assume for the sake of contradiction that q over square root 2 is rational. Then there is p in the rational such that q over square root 2 is equal to p, but that implies that square root 2 is q over p, which is a rational number, and that contradicts the fact that square root 2 is not rational. Therefore, q over square root 2 is a real number that is not rational, and it's between x and y. All right, so that's the proof of the last theorem. And now here, like I said, this is a pretty long and involved proof, so I'll go through it kind of slowly, and I'll refer back to all the things that he refers to so as we go along. So here's the proof of theorem 5.5.9. Let me just remind you of what the theorem is, because it's been a week or so since I posted my summary for section 5.5. Let me just go down. Okay, here it is. Theorem 5.5.9 is the existence of least upper bounds. It says let E be a non-empty subset of R. If E has an upper bound, then it must have exactly one least upper bound. Okay, so here's the proof. Now this is Tao's proof, but like I said, I filled in all the details because really Tao's proof isn't really a proof. It's more of a outline of a proof. So this is following his outline, but with all the details filled in. Okay, so let E be a non-empty subset of R with upper bound M. Then proposition 5.5.8 implies that E has at most one least upper bound. Let me show you what 5.5.8 says. That's this one, uniqueness of least upper bounds. Let E be a subset of R. Then E can have at most one least upper bound. Right, we proved that in the section. Okay, therefore, we must show that E has at least one least upper bound. Therefore, if it has at most one upper bound and at least one upper bound, it has to have exactly one least upper bound. Right? Since E is non-empty, we can choose some x0 in E. There are things in there, right? Let n greater than or equal to 1. Then by the Archimedean property, there is an integer k such that k over n is greater than or equal to m, which implies that k over n is also an upper bound for E. By the Archimedean property again, there is also some integer L such that L over n is less than x naught or x0. Therefore, L over n is not an upper bound for E, and this implies that L is less than or equal to K. All right, by exercise 5.5.2, let me just show you what that says. That's the one that we proved up above. Excuse me. All right, that's this one here. It's kind of long to read out, but anyway, hopefully you guys remember because we just did it, but this is what he's referring to by that exercise. All right, there's an integer m sub n, L less than m sub n, less than or equal to k, with the property that m sub n over n is an upper bound for E, but m sub n minus 1 over n is not. In fact, exercise 5.5.3, again, maybe I won't show that again because we just did it, but by exercise 5.5.3, that implies that this m sub n is actually unique. This gives a well-defined and unique sequence, m1, m2, m3, ... of integers, with each of the mn over n being upper bounds and each m sub n minus 1 over n not upper bounds for E. Right? Then if we choose capital N greater than or equal to 1 be a positive integer, and let n prime greater than or equal to capital N be integers, since each m sub n over n is an upper bound for E and m sub n prime minus 1 over n prime is not, we have the inequality m sub n prime minus 1 over n prime less than m sub n over n. Tao asks the reader to prove this in the middle of his proof outline, so I just did that down here. Here's the proof that happens. For each n prime greater than or equal to n, capital N, there's some y in E such that m sub n prime minus 1 over n prime less than y, less than or equal to m sub n over n for each n greater than or equal to capital N. So that proves that little statement there, right? And then also, Tao doesn't show the algebra here, but I did it out in detail so that you can see where everything is coming from. Okay, then we have m sub n over n minus m sub n prime minus 1 over n prime greater than 0, right? That's because of this inequality that we have up here. And that implies m sub n over n minus m sub n prime over n prime plus 1 over n is greater than 0, which implies that m sub n over n minus m sub n prime over n prime is greater than minus 1 over n prime, which is greater than or equal to negative 1 over capital N. And similarly, the fact that m sub n prime over n prime greater than m n minus 1 over n implies m sub n over n minus m sub n prime over n prime is less than 1 over n, which is less than or equal to 1 over capital N. So that means that negative 1 over capital N less than or equal to m sub n over n minus m sub n prime over n prime less than or equal to 1 over capital N. And that implies that the absolute value of m sub n over n minus m sub n prime over n prime is less than or equal to 1 over capital N for all n prime greater than or equal to capital N, which is greater than or equal to 1. Then the sequence of m sub n over n going from 1 to infinity is a Cauchy sequence by exercise 5.5.4. We did that one a few minutes ago as well, so I'll skip showing you that. Okay, since each m sub n over n is a rational number, we define S to be the formal limit of the terms of the sequence mn over n going to infinity. Exercise 5.3.5 implies, well, actually, let me show you what that exercise says first. If I can find, where do I have? Here we go. 5.3.5 is this proposition here. The formal limit of 1 over n as n goes to infinity is 0. So by that exercise, where was I? That implies that limit as n goes to infinity of m sub n minus 1 over n equals limit and m sub n over n minus 1 over n as n goes to infinity, which is the limit of m sub n over m minus the limit 1 over n, and that's equal to s minus 0, which is the same thing as s. Okay, so that gives us that the limit of mn minus 1 over n is also equal to s. Next, we show that s is an upper bound for E, so we're almost there. Let x be an element of E, then x less than or equal to m sub n over n for all n greater than or equal to 1. By exercise 5.4.8, that means that x is less than or equal to the limit as n goes to infinity of m sub n over n, which is equal to s. Let me just show you exercise 5.4.8. That's this one here. Let an be a Cauchy sequence of rationals and let x be a real number. Show that if an less than equal x for all n greater than or equal to 1, then the formal limit of an is less than or equal to x. Similarly, show that if an greater than or equal to x for all n greater than or equal to 1, then the formal limit of an is greater than or equal to x. So we actually use the second part here. So by that, let's see, where are we? Over here. So by exercise 5.4.8, x is less than or equal to the formal limit of mn over n, which is we define to be equal to s. Okay, lastly, we show that s is a least upper bound. So that's what we need for to show that something is the least upper bound. It has to be an upper bound, and then it has to be the smallest upper bound. So this is the last part. Let y be an upper bound for E. Since mn minus 1 over n is not an upper bound for E, y is greater than or equal to mn minus 1 over n for all n greater than or equal to 1. Then again, I won't show it again, but by that same exercise, 5.4.8, y is greater than or equal to the formal limit of mn minus 1 over n, which is equal to s, as we've shown. Therefore, s is less than or equal to any upper bound for E. Therefore, s is a least upper bound for E. Therefore, not only does the non-empty set E that's bounded above, not only does it have at most one least upper bound, it has at least one upper bound. Therefore, it has exactly one least upper bound. Okay, and that's the proof of that big theorem. Okay, so like I said, that's the end of the exercise set for 5.5. We'll move on to, there's one last section, and it's relatively short, 5.6. So we'll do that we'll do the exercise set for that, and then once we finish with chapter 5, we'll come back around to do Spivak. I did also want to say, I mentioned this a while back, but I don't know how many people watch my vlogs, but I said once I finished chapter 5, I was going to give a sort of my view of, or my opinion of Tao's book up until the end of chapter 5. That doesn't mean I'm not going to finish Tao. I will. I'm going to finish Tao after we finish Spivak, but I just want to give a little bit of my opinion of what I think so far about Tao. This way, if you're thinking about picking up a copy, at least you'll know what I think about it. So I'm going to end the video here. I'll see you guys in the next one. Let me know what you think down below. Give me a like, subscribe, all the YouTube stuff. I'll see you in the next one, and keep learning, everyone.